And there's quite a lot of other practical things that we need to do from where we are today to approach that vision of 1 trillion units deployed. And there's been quite a lot written about scaling, slowing down in the semiconductor industry. And obviously scaling has been something that has really driven innovation over the last sort of, well, certainly the 20 years that I've been on this planet. Maybe longer. So a lot about whether that's slowing down. I want to introduce a gentleman from ARM's research that wants to talk about whether he agrees with that. Greg Yeric is an ARM fellow. He runs the Future Silicon Technology Group in ARM's research, and so he's going to come here to share his opinions on whether the future is doom and gloom or whether there's actually a semblance of an opportunity for us ahead. Welcome, Greg, to the stage.
Thank you very much. Pleasure to be here. I have the privilege of working in the Moore's Law area at ARM. It may surprise you that we have about a dozen people at ARM working specifically in this area. We don't make chips. It surprised the TechCon registration. I had to register as an other. But there's a lot of interesting and necessary work going on in this area. I hope to talk to you about some of the specifics in the next 15 minutes. Now, the title of my talk, Where Are We Going? That really addresses a lot of the debate that's been going on, even up into the popular press, about Moore's Law. There's been some opinions that 28 nanometers was the best node ever, everything's done after that. There are other opinions that everything's fine. I'm not picking on Intel, they have nice graphics. All the founders will tell you the same thing, everything's doing well. In reality, 28 wasn't the best node ever. We're continuing to scale costs. We have a good cost story. The story is more like the straight line that you see on the right, but there are some big asterisks. There's some very interesting asterisks. So I wanted to talk to you a little bit about what's going on under the hood. And way down in the hood, if you look at standard cells, for instance, what's happening right now in the FinFET era, if I have a cell A and I want to scale it to the next node B, I would scale it by 0.7x. That's my Moore's Law node. Unfortunately, we're also in this era where we have to do increasing amounts of multiple patterning on the wafers to get to these pitches, and that's expensive. Practically, if you do an exact Moore's Law node shrink, you might find that you bumped up a cliff in the pitch cost area right up onto a new cliff where it's not really a good story for that node. So what you might end up doing is backing off the pitch a bit, backing off the cliff, and then finding some other way to get the transistor density up. And in the FinFET regime, the first, second, third generation of FinFETs, that's exactly what we've been doing. If you watch the pitches, they're not scaling like you think they would. But in the standard cells, we've gone from larger numbers of tracks in the cells to fewer and fewer. Commensurately, we've gone from 4 fins to 3 fins to 2 fins in these cells. We need the transistors themselves to really kind of kick it into overdrive to get there, but that's your story for second, third generation FinFETs. Now, you don't have to be an expert standard cell designer to realize we can't keep doing this very long. 1 fins would make a lot of circuit designers' heads hurt. 0 fins probably not work except for power. So I want to talk more about where we go from here, and I've highlighted one of the topics in yellow. In general, I'll call these topics scaling boosters. So if we can't get where we want to go with pitches, what can we do that help designs get higher transistor density on the wafer? And this one topic that I highlighted in yellow, in the standard cells I've highlighted now in red, dead space. There's a lot of dead space in these standard cells. For the whole 51 years of the Moore's Law era, we've never been able to put a contact to a gate over the active devices. I highlight in red the word laughable because when you do look at the options, over the last several years, I've asked the foundries, what about this gate contact? Can we maybe do something about it to get some of this dead space out? And I have literally been laughed at on multiple occasions. What I'll tell you now is there's a lot less laughter because the options are slim. So we have to start thinking more in these terms of how do we do these so-called scaling boosters to keep the density going. So potentially with this particular technology, we could hypothetically see a 5 nanometer technology that's a 5-track standard cell with 2 fins in it that actually works. Still hypothetical, requires a lot of work. The work also is not just coming from the wafer providers. These are interactions with how the design works with the transistors. And more you see this, what I call DTCO. The design needs to benchmark and weigh in on the effectiveness of some of these non-traditional scaling boosters, and hence you start to see why people at ARM might even start to be concerned about the process technology. Now, if you're adding all this up in your head, you're thinking quadruple patterning and the pitches and everything, and it's not working out for you, I do have a word of caution in this animation. So this animation is the speed at which 7 nanometer steppers will step across a 300 millimeter wafer, putting your great chips on the wafer. That's a full 50% faster than 28 nanometer steppers working right now. So you often make an error projecting the future using the parameters of today. There's continuous improvement throughout the industry. It's not just the stepper people, the etch people, the resist people, the people making the lasers. Everything's getting better. They have vested interest in this, and that helps the math a little bit over the edge to justifying a realistic 5 or maybe even a 3 nanometer technology. So to summarize on cost really quickly, yes, if you look at wafer cost and pitch, you could see that Moore's Law is over, definitely slowing down. The trick is a lot of these extra things I'm lumping into scaling boosters. This is the active area in the industry. There is one asterisk, EUV. EUV didn't quite make it for 7 in a lot of the foundry technology nodes. It is really needed for 5. So if we don't get a good EUV technology at 5, I might have to come back and be a little less optimistic. But keeping pretty good progress in that area as well. On the scaling booster side, there's a whole lot of activity there. A good way to summarize one of the key issues, though, is a lot of these are one-time tricks. So we have had a long history of lithographically shrinking the pitches and the Denard scaling of the transistors and what have you. That's having to give way to these, having to decide on these one-time tricks or multiple sets of one-time tricks. That's the change management challenge that's going to happen in the industry. And it's not just the foundries or it's not just the equipment providers. This is a stacked problem where we have to look at systems and circuits and how they interact with the devices. That's one of the big challenges going forward. So I mentioned Denard. Most of y'all are designers out in the audience. Cost is important, but you're really concerned about power and performance. Unfortunately, I have to say that we're not in the Denard scaling regime anymore. That era is gone. In any of the modern nodes, in fact, if you look all other things being equal, I will often be able to take a technology node, call it 7, make the gate pitch bigger, make the cells bigger, and end up with a smaller chip that runs faster. So we're technically in this reverse Denard era now. And as that pressure gets more and more intense, I think what you're going to see is more pressure to kind of bifurcate the technology nodes, find a high performance, higher cost, lower cost, higher efficiency. That pressure is going to increase, and that's going to be more complexity to manage, potentially. Could I go back a slide, please? Thank you. On the transistor side, that really drives a lot of the power and performance. What you should take away from this picture, I borrowed from Applied Materials, is there's a lot more colors and shapes as you go forward. So what we're away from the Denard scaling. We've gone into the FinFET. The FinFET may or may not make it to 5 nanometers, probably not to 3. What you're looking at is new transistor architectures, but a lot of new materials. Those are the colors. And that is the story, going from Denard scaling to dimensional scaling, the FinFET kind of stuff, to really materials engineering. And to underscore that, here is a small list, not complete, of materials being investigated for 2-dimensional FETs, which are one of the big candidates for 3 nanometers. You may have heard of graphene. You possibly might have heard of molybdenum disulfide. But this is the complexity we're managing. It's all about bringing materials in to solve some of the scaling problems we need. So I only have 15 minutes, so I had to summarize the wire scaling in one picture. This is my favorite failure analysis picture ever. And in reality, this is probably one of the least optimistic parts of the chip manufacturing. The scaling situation for the wires is difficult, and most of the very innovative stuff that's been talked about for 5 or 3 is really about treading water and not really fixing the scaling problems, just treading water and keeping R and C going in some kind of direction that's suitable. Again, It's all about materials. So I'm not making this up. There is an element called ruthenium. It's going to start showing up on your wafers, and it solves some of the resistance problems. And as designers, one of the things you'll see is it's not really as much about, only about the wire RC, but it's getting up to the wires. The contact and via resistance is starting to truly influence power delivery and the signaling. So that's transistors and wires. Things that could come onto the wafers that would help us in the scaling story. There's two big ones that I feel pretty strongly about. One is finding a better memory, SRAM. I talked about the standard cells. The SRAM scaling is actually a little more pessimistic story than that. If we did find a material that could supplant SRAM, maybe higher density, maybe non-volatile, that would be a big story. Nothing's quite there yet, but a lot of activity. And again, it's a lot of materials research. On the 3D IC side, I like this summary graph from IMEC showing the progression as we get more and more density into the 3D IC technologies. Today's technology, a lot of great success stories. You've seen the FPGA story from Xilinx. Here I'm showing NVIDIA claim that they're getting a 3x improvement in their efficiency by going to the existing 3IC technologies. That's not cheating Moore's Law. This is a quote from the paper. It's part of Moore's Law. We're allowed to break the chips up. Going forward, if you look at increasing density in interconnects, now you're talking about blocks on a chip. And this looks really attractive on a PowerPoint foil when you look at the needs of a big core wanting to go fast, a small core wanting to be efficient. Memory would like to be low power, low cost. The analog and RF is an obvious story. Many analog functions don't want gate to scale down, they get worse. So on PowerPoint, this is great. When you get in the details, you will be tempted to laugh. It's difficult. These are big things, supply chain issues, all kinds of stuff. But remember, people were laughing about that gate contact, and they're not anymore. So it's this block level, there is a lot of opportunity to optimize power performance and cost with the right technology and the right ecosystem improvements. Going forward, this is getting more into the chip level research that I actually work in. Machines that can bond wafer to wafer at the accuracy that would allow you to consider standard cell partitioning are coming. They're being announced in the roadmaps, and they're definitely coming. Here's a paper from my group that's going to be published next couple weeks at ICCAD. This is standard cell level partitioning of an ARM core. Just as a summary, you can drop some of the wires, you actually drop some of the area, and you can help pay for the technology. It's not necessarily full cost because you're getting lower area, and you get performance increase. The big question is, this is a one-time trick. Is it really enough to justify it? I can't weigh in at the moment. A lot of the issues are we don't have CAD tools that really allow us to fully exploit the situation. We need to go through a lot of those issues still. And then ultimately, if you really want to hurt your brain, you can consider the fact that this picture of transistors, this is technology we actually can do now. This is a CEA Leti, they call it the Cool Cube. But there's a lot of interesting possibilities of NMOS over PMOS, memory over logic, efficient transistors over high-speed transistors. A lot of really good options way out in the future. Maybe not even 3 nanometers, but the technology is being proven and is actually looking pretty good. Okay, so I've talked about a bunch of really crazy, complicated stuff. And those of you that are in charge of companies are realizing that it's a lot of R&D. So as an industry, this is one of the big issues we face, is bringing this technology in. So if I could lump us in industry in a box in the red line, our job is to extend this red line, this slowing of Moore's Law, and then somehow we need to bring in some innovative technology to pick up the ball and keep moving into the next decade. So that is a challenge for us. What we can do, what I found, I work a lot in this research box, is there's a lot of really good device and materials research out there by people who don't really understand what designers need. So we can contribute a lot in accelerating the understanding of this and bringing in new materials with proper benchmarking of the technologies and more directed research. To give you an idea of some of the things ARM is doing in this space, in this theme, many of you might know about the M0 Design Start. Universities can download the M0 for free, do design studies, got at least 150 downloads going so far. Last year, big in my space, we joined the SRC. I was an SRC fellow in graduate school, so I'm a little biased, but I think there's very good students and researchers going on in the Moore's Law technologies here. We just started our first research summit this year. The next one, I've got the date of the next one up. This is an invitation conference with the academic researchers, specifically looking at a lot of these approaches. And I've just given a few from this year that were specifically Moore's Law topics, but a nice collection of research to talk about. Specifically in my group, you might be surprised that an ARM collaborates with an ASML, the lithography tool company. But we have common interests and questions, and we find it's a very productive relationship. And this is from a keynote of ASML back at ISSC 2013. Big one again for my group is we joined IMEC this year. IMEC is the industry consortium that really works on a lot of these scaling boosters, figuring out how the rubber is going to meet the road. They have a 300 millimeter pilot line, they have an EUV stepper. Most of your companies are members, so I'm glad ARM can join you now. And I can tell you, we just had the first partner week last week. That's what I came back from to hear. I can tell you that ARM is going to contribute very nicely in this idea of benchmarking design. So there's a lot of these scaling boosters that need a little bit more benchmarking to understand how to down select and get to the right answer. We just joined this year, this is brand new news, we joined the System X Alliance. That's a Stanford, very good systems work, but all the way down into new non-volatile memories, carbon nanotubes, lots of stuff I care about as a device researcher. Not directly related to that, there's a paper we got accepted at IEDM, which is the big device conference in December. This is exactly what I was talking about. Letting the Stanford researchers come into ARM, evaluate some of the 5 nanometer candidate devices in an actual ARM core architecture and see, when you really bake it all out, do you get to good answers or not? There's a lot of dilution, of course, in the design process. In a broader academic context, we partnered with Arizona State. Arizona State now puts out a full 7 nanometer PDK that's available for free to academic institutions. So there's no excuse for an academic researcher not to put their fancy new device to task in a somewhat representative 7 nanometer technology. Here's a paper showing the assumptions. And lastly, I didn't quite get to TechCon on some actual information for you, but just to continue the theme, we are looking at even the materials research. So when we do find a university researcher that has an interesting material, in this case the memory, it's actually pretty straightforward to consider. We have the design expertise to evaluate something like that, see if it really makes sense in a memory instance, and then actually help get it through into equipment suppliers and into the industry to evaluate in a real nanometer node. So maybe next year at TechCon we'll talk about this project, but as a theme, you can see this branching down into the materials and really having a design company like ARM help bring some of this to proof of concept. Okay, so in summary, yes, if you look at pitches and wafer cost, Moore's Law is a tough story, going to 5 and going to 3, but a lot of these scaling boosters, there's a lot of activity here. We feel relatively confident that we can make a rational 5 nanometer node. We don't exactly know the right answers, but there's enough tools in the box. 3 is a question mark if you ask most people. Again, it's a little bit more radical change, and we have to evaluate, do we want to bring in some change that actually starts to affect the designers? On the power and performance I mentioned, that's actually maybe even more challenging than cost, especially performance. And again, the theme there is it's really about the materials at this point. We've run out of the device scaling, we've run into problems, but there are materials that can really help the story there. Another theme that will come out, a lot of it will be hidden to you if you're not directly working the wafers, but is a huge increase in heterogeneity on the wafers. So while a lot of it is hidden to you, I think it behooves you to understand what's going on down there, because you can in many areas exploit that. So if you start to have different kinds of transistors, different kinds of wires on the same die, or in the 3D IC realm in the same package, you can start to exploit that and get to better answers. And then, the big issue for our industry, I mentioned a lot of these are new materials are tough. These are one-time changes that require a lot of work to vet. And that managing what amount of change to put in at the right time is key. And that's not a decision that can be made by an equipment company or a foundry alone. These are things that really affect design and even the system. So we start to see moving from what I call design technology co-optimization to system technology co-optimization, where everybody has to get together and really find the right path, given the complexity of the challenges. Quick talk. Among the things I didn't talk about, the IoT, I feel strongly that Moore's Law should get a lot of credit. We wouldn't be talking about the IoT without the Moore's Law progress, and specifically things I call children's of Moore's Law. So if you consider the patterning we've been able to do, we've gone from microns down into nanometers, and now we are able to make features that would allow sensors to do things like smell and taste. So it's not about just reducing cost per function, but we're enabling entirely new functions that didn't exist before. And you'll probably see that in the next talk when we can get into molecules and proteins, and we're talking about a lot of things that can really affect healthcare in a positive way. And then lastly, lots of wacky things, but the key thing to take away is, yes, getting into nanometers is difficult, but once you get into nanometers, you can start to bend physics and come up with new, interesting ways to make computer chips. Plasmonics is a good story there. A lot of things where you can exploit the fact that we can make these so-called metamaterials. All right, thank you very much.
Thank you.